Exactly. But that's actually what the teleporter did on Star Trek. Yeah. It would take available matter at the other end and just superimpose yourself through it. Freaky if you think about it.
Yeah, but
it's all, it's not real. So, yeah, it doesn't really, it's not really freaky.
People say that that's fine, but how do you,
what's that?
Because you're cloning yourself, right? You're absorbing your matter and then moving it through something.
Oh, yeah, okay.
And
Chief O'Brien did what with teleportation? Well, no, it was Dr. McCoy didn't know.
Because matter is just matter, it's not your memory.
Scrambles your particles around. Oh my God. All right. So I've got the practice test.
Question.
Yay.
Page 468. Number 42.
Yeah, 42. Yeah, 42.
You're like, I don't even know how to do that shit. That's insane.
perhaps that is the ultimate question.
Exactly. It is the answer.
I mean, luckily my WebAssign definitely gave me the answers to most of it, but I still want to know how to do it.
Oh, I love this. All right, good. This is kind of awesome. So let theta, S, and H be in the figure. Assume the Earth is a sphere. Alright. So guys, this is 42 in section 6.4. It can't be 6.5. Alright, so they define my stuff here. So I got this satellite here. So here's how far it is.
Never again.
I was honest with you.
You didn't say anything.
Exactly.
Bill Clinton's way of being wrong.
I can't make this notebook.
And H is just this piece here. Okay.
Oh, never mind.
All right.
I think I figured it out.
So express the angle theta as a function of height. So what's the relationship here? In fact, they kind of help you out a little bit here. Do they give you that? No. So what do you think is true about right here? They don't say this, but what do you think is true about?
It's a right angle.
Yeah, it's got to be a right angle. In fact, that's why that's the point that you can see the furthest to. They're kind of related. So that's part of something they really should have told you. And then you got this triangle here. That this, of course, this much is the radius. So you're trying to figure out H as a function of theta. R is going to be a known amount, so it's not really a variable. S is going to be a known amount, it's not really a variable. Theta is going to be my real variable that controls all of those things, right?
Yeah.
This is not anything on your problem at all.
Oh, okay. So, I mean, what's one relationship I can write? I mean, do you
Why
guys...
couldn't you, no, this question.
What's up?
Why couldn't you just, see I didn't see this before, but why couldn't you just set it up like the area of a triangle and then subtract the area of the sector to do something?
To do what?
I don't know, find your H.
The H is sitting inside of a shape that I really don't know too much about with the area, right? The H is sitting inside of it's not a triangle it's sitting inside, it's sitting inside of this shape. So if I knew an area formula for this, then maybe that would help me out. An area formula in terms of H?
But you do if you take it and you subtract the
Sector.
conic, whatever, the sector area.
So you got your triangle here.
Yeah, and then you draw that down. That's a triangle.
So use the sector.
Yep, and then you subtract
You can get the area of a triangle.
Yeah.
And then subtract the area of the sector and get this area, and that area helps you get this out.
It doesn't.
Thank you. Okay, let's stop going down dead-end roads. That was my point. We don't know an area formula for that shape. If we did, in terms of H, then hey, that'd be awesome. If I knew the area of that, I could solve for H. I don't know an area formula for that curvy triangle.
Isn't that a triangle?
No.
Before you subtract the sectors.
Yeah, this whole thing here is a triangle. So that's a really good thing to use, right?
Find
Good.
the area of that. Wait.
And how does that relate to H?
So what
It's
about,
minus R.
What do you see the Pythagorean theorem of
H
the
plus
radius?
R.
We do have theta.
So I've got this beautiful right triangle,
Yeah, so
what about,
and they tell me what R is, don't they?
Yeah, it's 3,000.
Yeah.
960?
Yeah.
So this is R plus H, right? And this side, I've already labeled it, but that side, of course, is R.
960.
And this side I really don't care about, and this is theta. So what relates the stuff that I know and the stuff I want to know?
Secant?
Cosine.
Oh,
Cosine.
sure, secant. So cosine theta would be what?
R
R with H.
All right, solve that for H. And then you have H as a function of theta.
Oh, that makes a lot more sense.
So the first thing you look for always is a right triangle that relates what you want to know with some of the stuff that you know. That's what you always look for first. If you don't see that, then you go, oh shit, this might be something more complicated. So that's part A. So I'll let you guys do that part. Part B says express the distance S as a function of theta, and that's easy enough. I don't know why they made it its own separate thing. What's S in terms of theta? What in general? What's the formula for S?
Theta.
Yeah, S equals R theta. I guess part C, they're going to do something with the two of those. Yes, part C says, is everybody with me so far a little bit? I mean, there's the very obvious right triangle there. Not totally obvious, but you have to realize it's got to be perpendicular there. It's part of the reason why that's the point I can see to. It's perpendicular. Where am I at? Part B is almost not even supposed to be a question. It makes it sound like you got to do work, but no, it's just that there's the formula for S. Part C is where they merge these two. Part C says, I want S as a function of H. And of course, here you're going to have H as a function of theta, right?
Yeah.
So
Theta.
good. You can get theta as a function of H and then plug that in here. Not surprisingly, it's going to involve the thing that 6-4 is all about, which is inverse trig function, yeah. Let me see if you guys are sort of with me. So part A says function, it is a theta as a function of H. I thought it was H. This makes a little more sense to me. So what's theta as a function of H? What do you have to do to both sides to kill that?
Inverse.
Yeah. Think, I know, is it the one about cos? No. Take the inverse cosine. So theta is the inverse cosine of this. Or you could do inverse secant if you want to. Secant would certainly still work here. Would just flip that ratio, right? Then you plug that in there for part C. Because now S would be a function of H. Because what's R again?
Radius.
And think of the Earth. And thankfully that's not changing. That'd be a little weird if it was.
So S is different. Isn't it R2 theta?
What's happening?
no, not for the.
Oh, that's just a formula. Okay, I was talking for this problem. Wouldn't it be two of those?
No, because theta, that's where I gotta be careful here. I knew there was somewhere I had to be careful with theta. Theta goes across this whole thing. So what should be here for this, just this triangle, exactly?
Not on the picture, it doesn't.
Oh, really? Did they draw it the wrong way? Oh, theta, okay. Alright, so it's the other way around. I just had it this way from the beginning. My bad. So theta is just there in the triangle, so of course if I want to get the sector, it's going to have to be the other way around. Twice theta. Yeah, so right here, since our angle is twice theta, cool. So now you take that theta, and you plug it in here. For part C.
And then it's just plug and chug after that. Right?
And then part D just says, part D starts giving you values. See, I wouldn't even put R's value in. It's just easier to work with as an R. Until I actually want to calculate some values. What's up?
So what do you? So as far as the C part, making S equals the function of.
Yeah. So okay. That's the question.
Right.
Now we know S is twice R theta, and we know that theta is
Right.
that. So just plug that. And now S would be a function of H.
And then put the
That
radius
makes a lot
there,
more
or
sense.
just
the way you
What's happening? The function is 2r
do
theta.
that.
Right.
So 2r's got to be there. And then I just replace theta with what it is. And then part D and E is going to be easy. Once you have the function, you can just plug values in. It's kind of neat to think, if you're standing on the beach, how far can you see? Not very, because then this height would be your height. So you can imagine if you were instead standing at on the cliffs at Torrey Pines, that's adding quite a few feet to your height. So how much further could you see? Relatively not that much farther. You'd have to get pretty high up there to be able to see even further out.
Can't you only see for like about an average of 7 miles when you're
Something like that.
flat on the
I
earth?
forget the number.
Closer to 20.
I thought it was 22.
Something like I don't know. I don't know. You guys know better than me.
Because after that,
The curvature there
Curvature, yeah,
or something.
22.
There you go. So if it's just you standing here and you draw these lines coming from your eyeballs, well, they're only going to make it so far. And you can actually do the work and see if it's going to be 22 or whatever it is.
Cool.
Or something else. I like that. Your face didn't match with what you said. Yeah. Cool. Yeah.
You can see further from them.
since I was using a different way, just the way I'm trying to go about it.
Oh, yes. Same thing. We'll just have it flipped because we're using cosine. So you're fine. Yeah.
5378.
Oh, cool. Yeah. So tuning fork. Blah, 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 blah. DT is the displacement of the tines in millimeters at time t. So, of course, we all know that when you strike a tuning fork, it actually moves a little bit. And that movement moves air molecules, which goes to our ears, and that's why it makes a certain sound. This is going to be in millimeters of displacement, so how much that fork moves after I strike it. And it makes sense, it's modeled by sine. Any motion that's periodic, that's like that, like the C, I'm going to get C. Something that vibrates, that can be expressed using trig functions, sine or cosine. Find the period of the vibration. So in general, if I have A, sine, K, how do we do this? Kx, and there's no phase shift in there, right? So you just look at that. How do you find the period?
A. Right?
And that divided by
You use K.
It's 2 pi.
Yeah, so 2 pi, so part A is just 2 pi divided by K. That should be easy enough, right? Well, that's which part of this was the trouble? Hopefully A wasn't. Which one? Part B? Oh, so here's the cool, the number of times the fork vibrates per second. So the period is, in fact, let me make this more clear here for this. So in general, it's x or theta, but here my x-axis is actually going to be related to what physical? Yeah, it's going to be time. So my period in this case is going to actually be a certain amount of seconds. So the period is always some length on the x-axis, and my x-axis here is time. So now my period is going to be so many seconds. So it takes so many seconds for it to vibrate one way and then the other way, right? So this is exaggerated and slowed down. So when you find the period, it's going to be a certain number of seconds per vibration, right? So all you have to do is turn that bad boy over to find the frequency, which is vibrations per second. Right? Frequency is measured in, anybody know? What is it? A frequency of 60 hertz. And hertz is actually per seconds. That's the official units of hertz. It's per seconds. Cool. So it tells you how many cycles does it go through per second. which is the exact reverse of what period is. Period tells you how many seconds does it take for it to go through one cycle. So you just got to flip that over. So whatever answer you get for part A, reciprocate it for part B. And then part C just says graph that function. Yeah. You got to be careful when you graph it. It's going to be
Big.
It's going to be going crazy. The 880 is going to make, well, 2 pi over 880 means my cycles are going to be very tiny, which makes sense. Right? It's going to be a higher frequency of sound in general, high frequency. So when you graph this thing, you probably want to, they give you a few pointers in the section, but you want to make your x-axis kind of like zoom more in, or somewhere in the middle, so you can see all those vibrations. Right? They don't give you any estimates. Basically, graph it. They don't give you any window help. Okay, so I'll let you guys try that out. You should see it going crazy. There's an example, I think. Yeah, example 6. That one's just 50x. And that's going really insane already. This one's 880 pi x. It's like 2,500 something, maybe somewhere around there. All right, it's crazy. What's up? Very cool. So example 6, really good to look for help for number 78, part C. Anything else from homework? Yes.
What we're talking about.
Yes, thank you. Which one?
Same what you were asking. I don't know if you remember what it was.
40.
Oh, yeah, 40.
40, yeah, good. All right.
What section?
Section 5.3. All right, so this is an example of a problem that if I don't hear questions on it, I get a little concerned.
I have a quick question.
Sure.
When you're trying to find the 42, what we just did, finding theta, what mode should you have this thing set to? Radians or degrees? Radians or degrees?
If you're trying to find theta, it doesn't matter. It's up to you. Whenever you have theta anywhere sitting by itself in a formula or something, or you have to graph it, you want it in radians because that's real. But if I'm solving like sine theta equals something, then I can have it come out whichever way I want it to. Right? I can have the answer come out radians or degrees. It's more important when I'm inputting numbers that I have the mode match what the numbers are. So if I'm inputting degrees, the mode better be degrees. If I'm inputting radians, the mode better be radians. But here I'm like, well, what do I want it to come out as? Just know what it's coming out as. If you have radians, don't say 1.2 degrees, say 1.2 rad. Right? Just be careful, yeah. Okay, cool. Remember the example, Jeff. Whole test.
What number are we doing?
I forgot. 40.
Sorry.
Section 5.3, number 40. The hard part about this one is the examples we were doing were where the phase shift might be pi over 2 and the new period was 2 pi. So then it's really easy for those to work together to see what the number's going to be. Here, the phase shift, what's the phase shift? Here's number 40. 3 plus sine 3. Yes, what is that? 2 sine. So first off, what part of that do I not care about to the very end?
The
Plus
3.
three.
They're 3 plus, right? So just basically it's not there until the end. I don't care about it. It doesn't do anything to me in the middle. I just lift my whole picture up at the end. So what's the new amplitude?
2.
2. What's the new period? What have they done for me that they actually, I don't like the way they wrote that, so I'm going to write it better.
1.
2 pi over 3.
2 pi over 3. How do you find the new period? Somebody else said that. 2 pi over k. And they've already factored the k out for us. That's nice. And real quick, if you see this, you can think it's sine 3 that you got to distribute.
Yeah.
Right? So that's crazy. They really mean that. So they have to be more. The period 2 pi over the k value. Right? Because of course if that number is more than 1, it's going to make my period shrink. It's going to be compression. So that work actually makes direct sense. And what's the phase shift?
1.
What to the left?
Yeah, 1 to the left. So it's going to start at -1, but then it's supposed to go how far past that? 2 pi over 3. You see what I'm saying? So those don't really go well together. So here's what you do. So let's do it this way. And there's a lot of other ways to do this, but in general it's good to do this. You have to do it this way if you're dealing with tangent, cotangent, that kind of stuff. You want to be careful. But I would start, normally I start, let's write this the way it is, at, of course for sine it started at 0. So now we already know we're going to start at -1 because it was 1 back. And I'm going to end,
Plus 2.
yeah, 3x plus 3 equals 2 pi. So if you solve for this, you'll get divide by 3, and then subtract the 1, you get 2 pi over 3 minus 1, which only makes sense. If I start at -1 and I go 2 pi over 3 past that, I'm going to end up at 2 pi over 3 minus 1. Let me just stop right there. So that work is really not totally necessary, but as a student, if I'm first learning this makes me feel a little better to be able to actually grind those things out and not have to just tease them out. Okay. Now, the next step is, do you just make this into a decimal? No, it'd be better not to. Because the actual numbers I use for the points doesn't matter. Right? What do we do next? Normally I go 0 to 2 pi, and then what do I get in the middle? I get pi over 2, pi, 3 pi over 2. Yeah. And the most important thing is, whatever a quarter of the way into your period is, it's going to do what the sine normally does there. Right? That's the important thing. So I can call the point A, B, L, Jeff, who cares? You just do whatever's supposed to do there. So the label of the point doesn't matter that much. How much of a step am I going to take? The whole period is this. I cut that into how many parts? 4. So the step size is going to be 2 pi over 3 over 4, which is
8.
pi over 6. If you divide 2 pi by 3 and 4, you get 2 pi over 12. Divided by 4 is times 1/4. Either way you look at it, you get over 12. So, what in the world is this weird ass thing going to look like? So it's going to start at -1. The next point is going to be how far away from that? Pi over 6 away. That's each step I take is going to be that big. So what is it normally? 0 to 2 pi. Okay, cut that in force. What's 2 pi divided by 4? Pi over 2. So I take the next step, pi over 2, and then plus pi over 2 is pi, and then, that's what we normally do. So that's all I'm doing now. I start at -1. I know the period. I cut that into 4 parts. Each step is going to be this big. So the next point is going to be -1 plus pi over 6. And all that really matters visually is that more than 0 or less than 0? And pi over 6 is roughly
half.
It's a half. I love it. Right? Pi is roughly 3 if you want to be. I don't care. All I need is a rough estimate. So it's going to be maybe right here, -1 plus pi over 6. Or you can put a decimal there. I don't totally care, but it's better not to. -1 plus 2 pi over 6, or -1 plus pi over 3. Is that going to be above 0?
Yes.
Yeah.
Why?
It's a little bit more than 3.
Beautiful. Pi is a little bit more than 3, so you know it's going to be just a little bit more than 0. So this will be -1 plus 2 pi over 6. And we just, who cares? We just call it 2 pi over 6, just to make a little sense. Then the next step will be -1 plus
3 pi over 6.
That's crazy. What the hell are you talking about? And then the last step, -1 plus.
4 pi over
And where was I supposed to end?
that.
4 pi over 6 is 2 pi over 3, so we ended where we're supposed to end. Okay, good. So it doesn't matter what the points end up being called. All it matters is you know where those stupid points are. And then you can put what this thing does there. So realizing we still have to do plus 3 at the end, we don't care about that yet. What does sine do at the beginning? And of course it's also amplitude too. Yes, sir?
How'd you know to divide by 4?
Because the regular thing we do is we go from 0 to 2 pi. And then the major points are quarters along the way. So we just want to recapture this idea of quarter steps along the way, these major important things happen at 0 or 1 or 0 or -1. So if I can just capture those zero, and of course, what am I doing? I'm pushing it in or stretching it out and then moving it around. But as long as I can find those quarter points, I know what the stupid shape is. Right? That's the whole idea here. That's why this isn't nearly as hard as it first seems or might currently seem. Right? Because all we're doing, once we know where these points are, I just fill in, of course, what does sine do at the beginning of its cycle? Zero. And then now normally goes up to 1, but now it's going to go up to 2. So you just do that. So the next thing it does is go there. It's not a reflection, right? So it's still going to attain its maximum. And then at the next point it goes to 0. And the next point it goes to its minimum. And the next point it goes to 0.
And then you draw.
Yep. You make probably a good idea here would be to make a dotted line. Because still I'm not done, right? Maybe make a dotted line. So then you got this guy here. And then all I have to do there is just take every point and raise it up by 3. So if I would have thought ahead a little bit, my scale, I would have made it a little different. Up by 3 is going to go in here. So you just take that point up 3, up 3, up 3, up 3, up 3. That one I can do. Yay. And then you fill it in with a solid line. Right? The last thing you worry about is that +3 or -2 or whatever's outside. Because you got to get the shape first before you move the damn thing around. All right, how do we feel about that? Yes?
So if it would have been cosine instead of sine, would you have started at 1 instead of
Yeah, cosine would have still had all the same stuff. If that's the only change, cosine just starts at its maximum and then goes to 0, and then the minimum.
Okay.
Do you see? It doesn't matter at that point as long as you got the major points. Then you care about is it sine or cosine. Yeah. Yes.
What you guys just said just confused me about the cosine.
Oh, well, so why did we put that there? Because that's what sine does at the beginning of its cycle. So if it was cosine, I would have put that point there. Because cosine starts at the maximum at the beginning of its cycle. That's all. Yeah.
Can you explain why the start and end, like those formulas matter for like cosecant and secant?
You mean cotangent?
Or cotangent?
Tangent. Well, tangent especially. The reason that you can just look at this and know where it starts is because it normally starts at 0. So, since it normally starts at 0, if I stretch it or compress it, does that 0 move? No. But if I start at -π/2 and I stretch it, that's got to go somewhere. And then if I move it, shit's going to go somewhere again.
So you do that formula for -π/2?
Yeah, so if this whole thing, if this was tangent, isn't it? So what would change if this was 3 + 2 tangent this stuff? No, don't make it worse. Right? Amplitude is not really there, but still, you could use this 2. What does tangent do at the beginning of its cycle? It has an asymptote. And then the next point, it actually normally goes to 1, because the next point would be the quarter, π/4. So this would actually not go to 1, it would go to 2. So you can still use this number to give you one more anchor point to fill the shape over. Are you with me? It's not an amplitude, because the damn thing goes to infinity, right? But it does tell you one more point, 2 more points, right? One will be 2 and the other will be -2. On the next quarter point after. So, no amplitude really. But the period becomes what now? What is it normally?
It's π/3.
Yeah, tangent is normally pi, so now it's going to be π/3. And the phase shift will still be 1 to the left. And then I definitely want to do this. It normally starts at -π/2. That's where the first asymptote normally is. So now, if I solve this, it'll tell me exactly where it should start. Now, and I want you to really understand, because you have to think in your head the stretch or compression plus the movement left and right, just do this.
Yeah.
It tells you exactly where to start. That one, I can understand why you guys would skip that. I would skip that too. If I know this phase shift and I know the period, well, it moves there and then it goes that far. Okay, good. But because tangent doesn't start at 0, freakiness happens. So if you solve this, divide by 3, subtract 1, you'll get -π/6 minus 1.
Why do you subtract 1?
Because I'll have a 1 there. Yeah.
And by start, you mean draw an asymptote?
Draw an asymptote there. I like it. And then where will its quarter points be?
Divide by.
Because again, tangent normally goes negative pi over 2 to pi over 2. So it's got those, and the most important point is 0. And then these points are semi-important. They normally go negative 1, 1, but now, like I said earlier, they're going to go negative 2, 2.
So really the main point you need to find is that middle point and your end point.
For tangent, yeah.
Okay.
But I still like using these as just more anchors to see how curvy it is, how quickly it's going up and down. Does that make any sense at all? Any sense? A little bit?
It's a little bit harder.
Yeah. So, I mean, just to kind of do this a little bit, my first asymptote would be at negative pi over 6 minus 1. Now, what's my step? How much I'm going to step around? What's my period?
Pi over 3.
So I'm actually going to step by
Pi over 12.
pi over 12. Right? So I can make this negative 2 pi over 12 to match up with that. Is that cool?
Yeah.
So then it would be negative 1
Pi over 12.
minus pi over 12.
So 1
Yeah,
pi over 12.
I probably want to make this a little bit bigger scale. Because then it would be negative 1.
Plus 0.
Good, right? So I should have moved that over a little bit so I had more room. You with me? Okay, maybe, let me do that real quick, just in case anybody's... So I can give myself a lot more room over here. So this is going to be negative pi over 6 minus 1. We know that because we did this work. We know where it starts. And then pi over 12 away will be, let's make that negative 2 pi over 12 again. Negative pi over 12 minus 1, and then it'll be negative 1, and then it'll be negative 1 plus pi over 12. I think I still need more room. Damn. Because the next one will be negative 1 plus 2 pi over 12, which is negative 1 plus pi over 6. Oh, I didn't do the end. But we would run into the end here anyway, wouldn't we?
Yeah.
But you could do the end and make sure that you run into the right place.
But the end would just be over pi over 2.
Yeah, you would just say 3x plus 3 equals pi over 2. So it would be pi over 6 minus 1, which would be we're just one more step away from that. So this, I do this for myself. There we go, Jeff. So that's the ending point. So there, what would be here?
Your other asymptote.
Another asymptote. Cool. And then here would be 0. And then this would go normally to 1, but now it goes to
Negative 2.
negative 2. And then this here would go to 2. So then that would be that, and then I would lift it up by 3.
And where did we get it going down to negative 2 from again?
Because normally at the pi over 4 mark,
2.
tangent of pi over 4 is 1, and tangent of negative pi over 4 is negative 1. So normally it's negative 1 at pi over 4 and 1 at pi over 4. The fourth of the way marks. I really hope to God, I know what it does a fourth of the way in. I know what it does a half of the way in, so forth. If I know that, and I identify the new points, it's just do what it does there, right? Does it normally go to 1? Is it twice? Okay, now it goes to 2. Maybe. Or not. Yes?
So if the only difference if it was a negative 2, it would just flip it.
Yeah, this would go, and not negative 2 would go to 2, and that would go to 2. So it's a negative 2. Those points are awesome in that respect.
Yeah.
You don't even have to realize, you just go, okay, normally go to negative 1. Oh, it's a negative 2, so multiply by negative stuff at 2. Yeah, you don't even have to
And
realize.
if it was a cotangent,
Then it would start that way to begin with.
and then you can,
Okay. So what you have to definitely know is, we all know sine and cosine pretty well. They're both 0 to 2 pi normally. That's easy. Tangent, cotangent. Tangents
pi
go
over
from negative pi over 2 to pi over 2. What's cotangent? Starts at 0, goes to pi. Those things you have to know, or else ain't no damn way you're going to graph a cotangent.
So for the start on a cotangent, you would start at 3x plus 3 equals 0.
Beautiful, right? And some of you guys might realize cotangent, then you don't need to do that just as much as you don't need to do it for sine and cosine, because it starts at 0. Right, so it's really only tangent that you have to do that for. But if you're still not comfortable with any of this, always do that. Right? It's just really nice. You just do this work and bam, it tells you exactly where to start. Thank you. Cut the period in fourths and it tells you how much to move by. And then you just put the shape on top of that. Okay. And if I had to do, if this said cosecant, I would shift this up by 3, and then I just put my little cups on top and bottom, right?
Yes.
I keep this one as a dotted line to hold through, and then I just put the cups on top and bottom. So if that wasn't there, just so I can do it, and this was a cosecant, I would just put, maybe you do better, and there would be an asymptote wherever it's 0, right? Because that cosecant is 1 over sine. Is that?
Yeah.
Because cosecant and secant, if you can graph sine and cosine, you can graph those. It's just one extra step. Put the little cups and their asymptotes in there.
Can you use sine to graph cosecant?
That's what I was just saying. So if that was cosecant, I would have first graphed what we did,
Okay.
and then just put the cups on.
Cotangent ends at pi.
That's one way to do it. You don't actually have to do it, but that, to me, is the easiest way to kind of do it.
Seems easy.
And it reinforces your sine understanding. Okay. Anything else from homework?
No.
Okay, I'll take that as a no. So let's go over some stuff we went over last time. Let me see. So last time we got into the inverse stuff. And if you still have that first handout I gave you about trig,
Yeah.
I don't know if I have any left for me. At the bottom of that, it actually should have the stuff we're talking about right now as far as domains. I can't remember if I put the inverse stuff in there or not. Oh, that's just for, okay. Thank you. So let's go back over. I didn't put the inverse domains down there. So inverse trig functions. The answer to an inverse trig question will always be an angle. Remember when I said the logarithm will be a power, log is a power, log is a power. Because that fed right into their properties and all this other stuff. So an inverse trig will always tell you an angle. So if I have, let's use the angle. If I have this, and of course it normally looks like this. In order for it to have an inverse,
Yeah.
we had to restrict its domain to
A certain thing.
a certain thing.
It's,
Of course, why does it not have an inverse currently the way it
it
is?
doesn't pass the horizontal line.
Yeah, it doesn't pass a horizontal line test. So if I started at negative pi over 2, start it here, and go to pi over 2, now does it pass a horizontal line test?
Yes.
Yes. Cool. All right. That, of course, we saw yesterday how it leads to problems. Not really problems, but just we got to be careful. Since we restricted the domain, the inverse can never give us back all the possible things that it could have been. It can only give us in here. So this ends up being sort of related to reference angle answers. And then we have to make sure we're in the right quadrant from there. So the inverse sign has range negative pi over 2 to pi over 2. Right. And same thing with cosine. Same idea, except of course for cosine, how would I have to cut it? So cosine does this stuff. Very sure. Yeah, cosine's nice. I definitely don't want to go back here at all because then it's running into itself again, right? It doesn't pass. So I have to start here, no question. And then how long does it take to go through all of its positive and negative possible outputs? Up to here, and that point is pi. What's up? How we doing? Yeah, this should be like an X. So here, the inverse cosine will have range 0. Thank you. And tangent, we looked at tangent. Tangent actually and cotangent both are easier. because they already tell us where we have to cut them, right? From negative pi over 2 to pi over 2 for tangents. Cool. Okay. So if you do inverse tangent, you'll only get answers in between those outputs. Yes, sir.
Why is it with the inverse sine or the inverse cosine you change the variable from theta to x?
Because what's the output of a? Let me write it like this. Watch this, right? Sine theta in general will it equal another angle?
No.
If you take the sine of an angle, you get a
Ratio.
ratio, which you could make it to decimal, which is a number, a real number. And what do we use to represent real numbers?
Variables.
Very, very specifically,
X.
x. Sure. So if I take the inverse sine of both sides, I get that. So the input for an inverse sine will be a real number. What's got to be true about that real number that I put in?
Gotta be positive.
No.
It has to be.
So what's the output of a sine normally? What's the range of a sine? What's it go from to? What's the smallest the sine can be? Think about the picture. -1. And the biggest? 1. So what's the smallest and biggest the input for the inverse sine can be? -1 to 1. So if I ask you what's inverse sine of 7 over 3, you are completely allowed to look at me and go, what the hell is that shit?
No.
What angle would I take the sine of to get 7/3 in an output? You can't, because the highest output I can get is 1. So this is bogus. This doesn't make any damn sense. Okay, maybe. Now, just to go off of something from yesterday, real quick, this actually does make sense for very limited values of x. All right. So when all right, we're working our way towards that, where we left off last time. How are we doing so far? Is that right? So if I said solve sine theta equals -1/2 with theta in quadrant 3, well, that's too easy. You should know what the angle is, right? So let me give you one I have to use a calculator. -0.79. And if I don't specify, you can have your calculator in radians or degrees if I don't specify. And I didn't specify.
No, I didn't.
All right, so theta.
-50.
Yeah, so when you plug it in, you get -50.
52.189.
Roughly degrees. I'm sorry. Is anybody who tried that, did you get that? Or maybe got radians. Anybody get radians?
9.91. Wait, no.
Whoa.
-0.91.
Yeah.
-0.91
Reading.
rad. So if you convert this to radians, you should get that. Right? How do you convert this to radians?
Divided by
That's a good little review. Let's see.
1 over pi.
Yeah, right now it's degrees. So you want the degrees on the bottom and the rads on top. Go ahead and make that into a decimal. So do -52.19 divided by 180 times pi. And let's see if it comes out to be -0.91. If it doesn't, one group of you did this wrong. Or maybe both of you, I don't know. 0.91. Sweet! Thank God.
Yay.
You guys with me? So, of course, we'd have to convert this, but if I put the calculator in a certain mode, it'll just spit it out to me in that form. So if I don't specify, you can do it either way you want to. Now, is that right?
Yeah.
Which quadrant is that answer in?
The
this.
That's in the fourth quadrant. I'm supposed to have the answer in the
Third.
third quadrant. And why could it be either one?
Because it's negative.
Because sine is negative in both of those, right? You should know sine is negative down here because that's where the y-axis values are negative. Because sine likes y. SOHCAHTOA wouldn't help you with that. Sorry. Banging on SOHCAHTOA. Alright, so how do I get this bad boy to be in quadrant
Plus
3?
90.
This is effectively a...
Reference.
And then just don't worry about the negative. I mean, if I did negative 52, it's here. Well, how big is this angle? 52.19. So how big do I want it to be over here? 52.19. So what if I do 52.19 degrees? I end up 180 plus that. 232.19.
Pi.
Or,
Pi plus.
let me stop right there. Are you guys with me here? The answer you get from an inverse trig will be related to a reference angle. Sine will spit out negative stuff at you. It's just telling you it's a reference angle in the fourth quadrant. That's all it's telling you. So you should turn it into the third if you need to. Because a positive is here, so the answer might be over there instead. Cosine, of course, gives you 0 to 180. So it really, if I get 120, I got to go, okay, that's a 60-degree reference angle. If I got to be somewhere else, I can then use that to be somewhere else.
Why do you add 180?
Because the reference angle for this is 52.
Okay.
And if I want to be in the third quadrant, I've got to go 52 past that way instead.
Okay.
So this gives me the reference angle in the fourth quadrant. I want to be in the third quadrant, so I use that same reference angle there.
Why did we add 90 when we're trying to go from the first quadrant to the second quadrant then?
We were doing cosine.
We didn't add 90. Somebody suggested it, and it works, but I didn't look at it like that.
Oh, okay.
I'd rather look at it all the same kind of way. You'd still look at the reference angle and then apply that reference angle to the other quadrant if you needed to. We'll do a cosine one here in a second. If it was radians, how would I convert that into the right quadrant?
Pi plus.
Yeah, so I want to go 0.9 rads past pi, so it'd just be pi plus 0.91. And at that point, you might as well just make it a decimal, right? Part of it's in decimal, make the whole damn thing decimal. Okay, it's 4.05. Right. So let's do a cosine problem. Same kind of way. So I want the cosine solved for theta with theta in quadrant. Oh, I got to pick on quadrant 3 all the time. Well, make it quadrant. Wow. You ready? I haven't put the problem on yet.
Yeah, like, okay.
You're like, I'm done. Oh. What you got, Jeff? I don't know.
And you didn't specify again on purpose, right?
Specify which part.
For radians.
Oh, yeah, exactly. I want to do both again.
I'm not sure because I'm trying to think of where that reference would be.
I'm going to pass out the practice test while you guys are doing that.
So we need to go minus that. So 2 pi minus. If you have it. It'd be 360 minus. Oh, yeah, because you want to try it 4. So add that.
Are you saying negative?
Except he wants to add the degrees. It would be better to do 360 minus.
I get it.
Yeah.
360 minus 4.
Several of you just don't get one. No, if you want, if you want, I can either email it to you or you can come to my office after class. I'll print you out one. I must have thought I was done and it just ran out of paper. That's my bad. So you guys back here, you with me? If you want a practice test, and if I were you, I probably would. Either just email me and I can email it to you, or come with me to the office after class. All right, so what do you guys? Oh, yes, these are. So cosine inverse 0.91. What do you get for the angle in degrees? Who did it in degrees?
24.5.
24.5.
Yeah.
And in radians?
20. Yeah.
0.43.
Yeah.
Okay. And of course, is that the answer?
No.
No. I want it to be in quadrant 4. So one thing you could do
60 minus.
is just say negative 24.5. Negative 24.5. But if I said, and I probably will, I want theta to be in that range. No, it doesn't allow for that.
360 minus.
Yeah, then right now it's here, that's a reference angle. You want it to be in quadrant 4, which doesn't screw with cosine being positive, right? So that's why you're completely allowed to do this. That's 24.5. I want this to be 24.5. So you have 360 minus 24.5.
335.5.
So same exact thing over there. Instead of 360, of course, in radians is 2 pi. So here I just say it's 2 pi minus 0.43. And then you can make that into a decimal from there. If you stop there, it's okay. Yeah.
So you were saying if it was negative, we'd have a problem, right? Because you couldn't have a negative in quadrant 1.
Oh, if this equation started with a negative, then the inverse cosine would have given me an answer in the second quadrant. Because that's where cosine is negative. So the real answer could be either there or the third quadrant. Because either one of those are where cosine's negative. So if I would have made this negative 0.91.
So it wouldn't have worked at all.
It totally wouldn't, of course. Let's do it. All right.
So would you have had to change the quadrant it was in, or?
Okay, yeah, that's what I mean.
We just did, didn't we? We do exactly what we just did. That's the answer.
No, he's saying that the way the problem is, would it work for quadrant 4?
Oh, of course not. No.
That's why
I'm sorry.
Yeah.
No.
Then I'd rewrite this, but I couldn't say that.
Yeah.
Okay.
All right, I got you.
Okay.
That's,
Confused.
but if it was just 2 to 3, then it would be the same thing.
Exactly. So if I said with theta in quadrant 3,
Then
that would be fine.
Yeah.
Okay.
Always in that.
So let's look at that last thing we were looking at. And, well, before we do that, let's do a nice visual problem here. So if I'm standing out here and I look and I measure the angle to Coles Mountain, let's say. So I'm standing here. Well, I'm laying on the ground, so I don't have anybody yelling at me about it. Oh, hi. All right. So this is actually a good point, but it won't do that. I measure the angle of elevation to the top of Coles Mountain to be. Sorry? These are my legs. I've made myself into a fish. I don't know why. I'm a fish. All right? I am Aquaman. I'm the lamest superhero. So,
What?
He is the one.
yeah.
all right. I'm sorry that I started that debate. Let's not go there. He is. He's accepted. Have you seen his own movie yet? No. And let's say I know that I am, and this happens. I know how far away I am. Do I want to climb? I've climbed in Coles Mountain, but if you're talking about a real mountain, you want to climb the damn thing necessarily? No. See how tall it is? Some of us might want to. Some of us maybe no. So if and very often, I can look in Google Maps and see how freaking far away linearly I am from the mountain, right? So I can get this distance very easily. You don't even have to leave the room. But I have to leave the room to get to this angle. So how tall would it be then if I know that I am, what you got, Jeff? Oh, let's say 13,000, maybe a little more than that. Let's say 19,000 feet away. So if I thought about it, I would have looked this up before class and actually gotten the real number here, but oh. So yeah, the thing relating what I know and what I want to know in this case is tangent. Now why did I do that? What I meant to do, I'm so silly. I want to make this an inverse problem. So take that 14 degrees away. That was an earlier problem. That's easy. So now if I know that Coles Mountain is, I forget how tall it is, but I'll see.
10 feet.
10 feet.
Exactly. Solid math and logic.
What? People jog up here?
Who cares?
Yeah, okay, we'll make it 1,500 feet. Sounds
That's
more.
pretty fucking low.
Definitely less.
Yeah, it's more than that, I thought.
Do it 25,000.
No, it's not.
25,000. Oh, let's climb Everest.
This is Mount somewhere else. Alright, this is Mount somewhere else. I'm in Springfield, and because there's a million Springfield. So again, but of course, I'm still gonna. If I want to know what this angle is, yeah. So I have tangent theta relates to the sides that I know. Now, if you wanted to, you could figure this side out, but why would you? Because that introduces one more place you could make a mistake.
Yeah.
I always want to try to use the numbers I know are right as often as I can. So the ratio would be
15.
over 19,000.
So what's the inverse tangent of that?
90 over 1900.
Oh yeah, it's trying to be 9. That's really bad. My 9s are now like my 5s, and my 5s are my S's. So good luck. 4.51 degrees? Or 0.079? So tangent is going to be a lot like what other trig function, considering, inverse tangent, is going to be a lot like what other inverse, considering its possible outputs. What are the possible outputs of inverse tangent? What are the inputs for tangent that we're going to use? No. What are the angle inputs?
Pi over 2.
Negative pi over 2, pi over 2. So the outputs for inverse tangent are negative pi over 2 to pi over 2. Sounds a lot like sine, right?
Yeah.
So it could possibly have negative angles that you have to put in the right quadrant, or this could have been a reference angle that you have to put in the correct quadrant. Same problems, right? Same kind of things you have to adjust.
Actually, we're pretty darn close.
Oh, good. All right. Crowdsourcing kind of. And
It's 1,594.
well, that, for us, that is exactly on. So screw it. They shaved the top off a bit. Okay. All right. So there will be some physical, visual problems. We got to figure out the angle, but you should be at this point able to set up the correct ratio, and then you just have to go one extra step. Do the inverse trig function. Right? We haven't done that before this section, but now we will. And finally, that last thing we did that is really important for future math classes. And if you don't have any future math classes, it's really important for this one. And that's how to handle something like cosine of inverse tangent of... now why can I do that?
Make a triangle?
Yeah, let's make a triangle.
That's how I can do it. Why can't I do what I just did? Did we have an earlier one, the 7/3, and we're all like, that can't be.
You make it
It's
a
tan.
triangle.
Because tangents outputs go negative infinity to infinity. So inverse tangent can handle any input. The outputs will be negative pi over 2 to pi over 2.
So you make it a triangle. Because that's
Yeah.
theta.
So this, and I really want to make this point. We saw this yesterday. The triangle I draw is not necessarily a triangle that exists anywhere. It's just a nice representation of what this could mean. And I'll get the right answers no matter what if I draw the triangle. But we saw yesterday, I had, one side looked like it was longer than the other, unless I used negative x's. And then you'd say, well, a triangle can have negatives. Well, it's not really a physical triangle. It's just a construction we make to help us do this kind of problem. So what can I construct from this?
A triangle.
Because what is the output of an inverse tangent? Angle. So this is the angle that's referencing.
Yeah.
So this means that the tangent of an angle would be 7/3. So who's 7, who's 3?
7.
7 to the left, 3 down.
Good, right? Because tangent y over x.
Yep.
And then, of course, this side, for the cosine, I'm going to need this side. So what's that going to be? And be real careful, guys. Can you just take any of these numbers and just throw them anywhere you want to in the Pythagorean theorem?
No.
Some people seem to think you can. right? But this side, of course, has got to be the side by itself because it's the biggest one. It's made of the other two being added, right? This is nice. You just add those 49 plus 9, 58.
Yeah, that's not
That doesn't really simplify anywhere, so I can just keep it there, right? And so what's the answer? What's the cosine of this angle? Now that I have a nice visual of it.
3 rad 58 over 58.
Yeah, good. 3 over rad 58, so it'll be 3 rad 58 over 58. I like it.
Cool.
Okay, cool. And again, let's try this again. Let's see if I can make one that's less controversial. Yes?
So, what would it look like if there was no tangent inverse? Inverse tangent, I'm saying.
Your question could be really, really deep, but I don't think you mean it that way.
I probably don't.
If there were no inverse
tangent.
tangent.
No, I'm
The
not.
world. But in the problem, what do you mean? If that just wasn't there?
If it was just tangent.
Oh!
Tangent to theta, for example.
Well, then that would be an angle. And then I could just plug in the calculator. Right?
It's
I
a
mean,
So-
but it looks exactly the same, wouldn't it? Like, if you drew it out.
Hell no. Hell no. I really want this understood. The only reason I could draw this is because this means, so inverse tangent, let's look at this really in depth, equals what? An angle. Good, theta. So how do I kill inverse tangent? I take a tangent.
Okay.
So I get 7/3 equals tangent theta, and that is this situation, isn't it? So if it's not an inverse, I can't do this, I can't make that triangle. I wouldn't need to make the triangle. You would just plug that in the calculator. Because there's no other really way to do it, because it's not an angle that I know. Right? 7/3 radians. I don't know that. With that said, if somebody gives me a decimal answer here, and I don't see this, you're losing all the points. Right? Basically. You have to do this work again. All right, calculator. Get me through this. No. You have to show me this work. I will give you some that you got to use a calculator for.
So would you ever do? I don't know if it's even possible or... Anyways, so what if you did give us just an angle, and then through using this, you wanted us to find the other portion. So
if I
tangent of 7, the inverse tangent of 7/3, right? Gets you 66.8 degrees, but then that's all we get. Now, changing that to the fraction, if we get some wild number. Would that?
changing it to a fraction, how do you?
Yeah, like this. So tangent to that, and then you get the fraction.
Oh yeah, no. 66.8. Now real quick. Yeah, do that for me. Let's try this out. What is the inverse tangent? Everybody get that? Chris has got 60-something degrees.
Yeah, 66.8.
So do inverse tangent 7/3. Now do cosine of that. I'm just adding stuff on top of yours, Chris. Huh?
0.39.
Yeah.
0.39. And what is 3 divided by the square root of 58?
Oh god.
It better be the same thing, right? Or else
Yep.
we're screwed.
0.3939.
Oh my gosh. Of course, on one level, it's like, well, duh. That's the answer to that. But of course, if you do it in the calculator, you can see what the angle actually is, plug that into that bad boy, and you get what this represents. Or at least the best approximation your calculator makes. This is the right answer. You give me a decimal, it can never be right, because you're never going to give me the infinite number of points it has. Okay. Oh, so one more, and we'll involve x's here. Let's see. And just to keep myself safe, I'll do that. I like it. I like it a lot.
Are you saying that that's over theta? You're saying
No. I'm saying that represents theta.
Okay.
So that's the theta that's in my triangle.
For a second, I thought you were being a fraction.
That would.
So essentially, for that triangle you just drew, like as long as you plug in the x minus 2 and over x into the correct place, the theta would be in either corner.
As long as you put it in the right place according to where you put your theta.
Okay.
So I would always put the theta in the base, because then it relates directly to y and x. So sine, of course, the top's got to go. Oh, you took it so deep. And then the x minus. All right, good. So sine likes y, so the top's on the y, the bottom is over the hypotenuse. To get secant, that's related to, so I need the last side, right? So then the last side is going to be the square root of this square minus that square. Here's one reason why I gave this to you. For some reason, the further people get in math, the harder problem they have with stuff that used to be really simple. What do you have to be careful about when you simplify this? This is not good enough. Yeah, but that negative's got to go through the whole thing, right? So x squared, you'll get minus 4x times the negative is plus 4x. Plus 4 times the negative is minus 4. Your x squares go away, which is nice. So what is the secant of that angle?
4x minus 4.
Careful. Yeah, x over square root of 4x minus 4. You could take a 2 out of it if you want to.
And then rationalize.
And then rationalize it, but this is fine.
okay.
So you would want us to rationalize that?
I'm not going to make it. If you want to, certainly. It's not wrong.
You always say rationalize.
I do.
With real numbers, right?
Just not that one.
No variables.
Just not this one. I'm trying to think of a number. This might not be irrational. Maybe 4x minus 4 is a square. No. So if you wanted to rationalize this, I mean, can everybody see where that comes from?
Mm-hmm.
Square root of 4 is 2, so you just take a 2 out. And then you multiply top and bottom by
X
X minus.
root of x minus 1. So you get x squared of x minus 1 over twice x minus 1, right? Okay, so the rationalization there works the same way. Alright. So that's the last idea in this section. 6.4. So just to really make sure everybody remembers, the test is only going to go up to 6.4. Homework up through 6.4 is due. 6.5 and so forth will be in the next test.
I'll just come up.
Okay.